Hello, welcome back. The topic of this video is the interaction of neutrons with matter. This is important to understand because it's going to have some practical applications later on. This builds on what we've seen in the last couple of videos, which is the processes by which charged particles interact with matter. Now, neutrons, of course, are not charged, so you think that they might just sort of barrel right through and not interact. Well, that isn't quite true, and we're going to learn why in this video. Here we go. So let's start again with this schematic of the atom. Of course, you get the charges, negative from the electron, positive in the nucleus. The neutron is going to come in here. It doesn't have any charge. It's going to come in and it would theoretically go right through. Sometimes, though, it can come close to the nucleus in here, and then you've got an interaction. So that's what we're going to study, neutron interactions. So there are two types. Number one is thermal neutrons. That's less than 0.02 electron volts. And number two is fast neutrons. So that's taken to be greater than 100 electron volts. And the interactions are different in those two regimes. So we're going to look at those. Let's look first at thermal neutrons, the slower moving neutrons. Interaction of thermal neutrons. So here's a neutron, and it comes in, it's going to interact here. In this case, I'm going to draw it with a hydrogen atom, one proton, comes in, undergoes an interaction. It's moving slow. What happens in this case is it actually gets captured by the hydrogen atom, and it gives you two as deuterium. Now there's some energy left over after this interaction because the binding energy of deuterium is less than the binding energy of the components that started out. So you've got some energy to put into the reaction. And that energy comes out in the form of a little bit of energy to the deuterium and most of it going into making a photon. So that's the way that one of the ways that thermal neutrons can interact. So a thermal neutron can interact with other constituents of matter as well besides hydrogen. And so to understand that and what's important medically, let's look at the abundance of different elements in tissue. That'll be relevant. So I'm going to list them: oxygen, carbon, hydrogen, nitrogen. Those are listed in basically the relative abundances. The cross-section for interaction of oxygen and carbon is small, so let's ignore those. But hydrogen and nitrogen, those have a larger cross-section, and hydrogen in particular has a big abundance in tissue, so it's important. We already talked about hydrogen. Let's go back over here. Look at the neutron interacting now with nitrogen. That's nitrogen 14, 7 protons. When that interaction happens, it actually creates a carbon atom with 6 protons, and so you're going to have an extra proton left over. And then there's some energy that's given to those two particles. Again, because the binding energy of these is less than the binding energy of what you started with. And so it's given to the kinetic energy of the particles. So those then are the two main interactions for thermal neutrons, interacting with hydrogen or nitrogen. And you can see that in both cases, it's not the neutron itself that's depositing dose, but instead the particles that come out. In the case of hydrogen, you get a photon coming out, deuterium. In the case of nitrogen, you have a carbon particle and a proton coming out, all at relatively low energy, and they deposit their dose locally. So there's another kind of interaction that happens with the neutrons. That's with the faster neutrons, higher energy, and that's a different type of interaction. So let's go back to the neutron and have it interact again with the hydrogen atom. Okay. In this case, it's a billiard ball type collision. So the two particles go off in different directions. It's an elastic collision. You can also have the neutron interacting here again, let's say with a carbon atom here. Then the neutron has some energy and the carbon has some energy. So again, it's a billiard ball collision. That's what happens with fast neutrons. So now I'm going to write a little equation that will describe the energy of these nuclear particles coming out. I don't know that you need to know this in this level of detail, but it might be illustrative. So I need to define some parameters first. So here we have the mass of the neutron, and it has some energy, and the mass of the nucleus. And then the energy of the nucleus coming out is given by this equation then. Okay, so there it is. And if you figure out what those numbers are, for a hydrogen atom, it gives about 0.5 times the energy of the neutron coming in. So in other words, about half of the energy of the neutron, if it collides with a hydrogen atom, is given over to the hydrogen. So it's a very efficient process. For carbon, the numbers are different. Here it is. It's 0.12, 12% of the energy of the neutron coming in. So much less efficient. So there we go then. Those are the two main interactions of neutrons. I'd like to just say a few words about how neutrons are relevant in the therapy context. So first we'll talk about neutron contamination in therapy beams. First example, a photon beam. If the photon beam has an energy greater than 10 MV, in that case you can get what are called photoneutrons. That is where a photon interacts in the vicinity of a high Z atom and produces a neutron. So this would typically happen then in the target or flattening filter or jaws of a linear accelerator, which we'll learn about later. Second example would be a proton therapy beam, which also produces neutrons contamination. And it depends a lot on the components of the system, how many neutrons are produced. Next clinical context where neutrons are important is neutron interactions in shielding. That often comes up in the context of door shielding. We'll talk about that in a future video. And then finally, neutron beams for therapy. So neutrons can actually be used to deliver therapeutic radiation. Here is one common way that these are done. A 50 MeV proton beam interacting on a beryllium target, which then produces fast neutrons. These neutron therapy facilities in the world, very, very few, actually, so I won't dwell on it, but it is a modality, and it was important historically in the 1980s. There was quite an effort to do neutron therapy. I will mention one more thing about neutrons, and that is boron neutron capture therapy. Again, it's a therapeutic neutron modality, but it uses boron to enhance the effect. So let me explain how that works. So to give some context, let me go back here. Let's look at the neutron interacting with nucleus, say hydrogen or carbon. So for hydrogen, the interaction cross-section is 0.33 barns, carbon 1.8 barns. That's just some unit that says how probable it is. But now let's look at boron. Well, the cross-section for that is 3,840 barns. So it's huge compared to hydrogen and carbon. The interaction there is boron plus a neutron goes to lithium, 7 lithium, plus an alpha particle. So it gives out charged particles that deposit dose. So boron neutron capture therapy, then you have, let's say, a tissue here, and you put a neutron beam, therapeutic neutron beam, onto that area. And then here, if you can get boron in, let's say in a vessel here, and maybe that boron, let's say, leaks out of the vessel through a leaky vasculature into the tumor, or maybe it's targeted in some way onto a particle, then the neutrons are going to interact there. They won't interact much in this other tissue, but they will interact a lot in where the boron is located. Again, this is a modality that's not really used now clinically, but has historical interest. Now, the final topic on this video, briefly, is going to be LET, linear energy transfer. And now that we understand charged particle interaction and neutrons and everything, I think I can have an intelligent discussion about LET. So LET is related very much to stopping power, the total stopping power, the energy loss, but it's a little different than stopping power alone. LET is actually the energy loss, but it's the energy deposited locally. So that's in a particular area of region of interest. Let's look first at heavy particles, and then I think you can understand this. In a heavy particle, the stopping power is about equal to the LET. So why is that? Well, you remember from the last videos that the radiative energy loss of a heavy particle is really small. It mostly loses its energy through collisions locally. So the LET, the local energy deposition in a small region where the interaction is about equal to the stopping power. It all happens locally. The situation is very different for an electron. So let's consider an electron. It's wandering around in tissue here. Let's say at some point it undergoes some really radiative loss, bremsstrahlung, and it makes a bremsstrahlung. Photon travels quite some distance potentially, undergoes Compton scattering, makes another electron which wanders around. Maybe it makes a delta ray at some point, a hard collision, and so on. So you see that there's an initial interaction site here, but the energy is not deposited locally, potentially spreads out over a large distance. So for light particles, the LET can be quite different than the stopping power. LET is what you're interested in, I suppose, because it's the local energy that is really going to control the biological damage. So we can talk now about biological damage because that's going to be related directly to LET. So I'm going to plot this quantity, relative biological effect, RBE, which can be assayed in biological assays, and plot this versus LET, and you'll see it increases as the LET increases, and then it turns over. Maybe that turnover is somewhat controversial because the high LET measurements are kind of hard to make. But basically, LET is going to depend on the particle type. And so if you look at different particle types, down at low LET, we have photons and electrons. The RBE, by definition for that is 1, very close to 1. Then as you go to different particle types, you have protons. Those actually have, it depends on the energy, as we'll see in future videos, but the LET is pretty low. The RBE is about 1. Okay, and then you go up, and here you hit the neutrons, the fast neutrons that we were talking about, and the RBE is about 3. Going up, you have heavy ions. Carbon ion is an example. And those have really pretty high LET. Again, it's energy dependent, but the RBE is high, and then alpha particles at the top. So basically what you're seeing here is the biological effect depends on how densely you distribute those damage sites and how much energy per unit path length is put down in tissue. That's really what affects the biological response of the system. All right, that concludes our discussion about neutrons interacting with matter. I'm going to leave you with a little further reading if you want to understand more about the physics of neutron interactions, which is a deep and rich topic. And as we go on into the next videos, we're going to start to get more into applications-oriented things. This really kind of concludes the first section of what I think is this primer, which is the basic fundamentals of interactions. And we're done with that, and we're going to get into applications. So I think you've learned a lot. Take a breath and pat yourself on the back, and we're going to move on in the next video. Thanks.